Yeah, in our last class we discussed the principle of operation of a pulse width modulated or PWM AC to DC converter. Okay. Our observations were, the first one is, if there are large number of pulses for cycle, the frequency of the predominant harmonic that is present in the source current increases. Okay. Second one is, a sinusoidal pulse width modulated technique can be used to determine the turn on or off of the switching devices. Okay. For a sinusoidal PWM technique, I told you that there has to be a modulating wave which is nothing but a rectified AC, input AC. Frequency is same as that of the supply, but the magnitude should be variable. There is a carrier wave which is a high frequency triangular wave. The frequency as well as the magnitude are held constant, okay, and the frequency of this model of the carrier is much higher compared to that of the modulating wave or the supply wave. So if there are n pulses for half a cycle, the frequency of the predominant harmonic that present in the source current is approximately n plus 1 into the supply frequency. Okay. I told you that as the frequency of the predominant harmonic increases, the filter components that are required to eliminate this predominant harmonic decreases, the size decreases. So higher the frequency, smaller is the size of L and C, but then as the frequency increases, inverter losses increases. So therefore the frequency of the triangular wave depends on the type of device and the power rating. Say for example, if the load is of a few HP, say 2 to 3 HP motor, and if I have a IGBT device which is fast, I can switch maybe as high as 10 kilowatts or so. But then if the power rating is of the order of say hundreds of kilowatt, and if I use GTOs, the frequency could be less than 1K, So therefore it depends on the power rating as well as the device. Okay. Now how to decide how to vary the output voltage? How do I vary the magnitude of the output voltage? See this slide. Magnitude of triangular wave is constant, but then magnitude of this sinusoidal or modulating wave, I said, should be variable. If the magnitude of this modulating wave is very small, you will find that device is off for a longer time and is on for a shorter time. Okay. So in the first quadrant, S1 and S2, if they are on for a shorter duration and if it is off for a longer duration, power supply to the load decreases. Whereas if they are on for a longer duration and off for a shorter duration, power supply to the load increases. Therefore, if I increase the magnitude of the sinusoid or rectified wave, the magnitude of the output voltage also increases. So there exists a relationship between the output voltage and the magnitude of the sinusoid. V naught is proportional to m, where m is the modulation index. It is equal to the magnitude of the sinusoid divided by magnitude of the carrier. Since AC is held constant, V naught is proportional to m, or V naught is a function of the modulating wave. Okay. So S1 starts conducting in the near the zero crossing of the modulating wave. Therefore, displacement factor is approximately 1. Okay. There are large number of pulses, so frequency of the predominant harmonic also increases. So I use a small L and C which filter this predominant harmonic. So it so happens that the fundamental component of the source current is approximately equal to the RMS value. So the power factor also improves. Okay. So the power factor of a PWM converter is approximately 1 unity. Now the question is, how do I get a modulating wave whose frequency is twice the supply frequency, magnitude is variable? Okay. One way is use a step down transformer and a potential divider. Step down transformer, rectify it, I will get a rectified sine wave, then I will use a potential divider. Now this is manual control, in the sense you need to change the magnitude or you need to change the potential divider, the position of the variable point, to vary the output voltage. The second one is you can digitally synthesize a sine wave. Okay. I will explain the working of this circuit very briefly. Okay. So what I did is I took a sinusoid, a center tap transformer, I rectified it, okay, a full wave rectification here. Then I gave to a zero crossing detector, nothing but an op amp. Then I got 2 pulses here at the zero crossing. Okay. Now I will digitize the rectified sine wave, okay, and I will store it in a EEPROM. Okay. Both 0 to pi and pi to 2 pi, and I will store it in the EEPROM. Okay. So if I divide this half a cycle by 256 parts, so in from 0 to 511 I store the rectified sine wave. Okay. Now this 0 to 511 locations should be addressed in this period. Okay. So I need to have a counter which addresses the EEPROM. Counter should start the 0th location at the positive zero crossing and at 511th position just prior to the next zero crossing. Okay. Now but then this n bit counter requires a clock. There has to be a relationship between this clock and the supply frequency. Okay. So if there are 512 locations here, the counter should get 512 clock pulses in this period. Okay. So what I will do is I will use a PLL as a multiplier. Okay. So n could be here nothing but 2 to the power 9, that is 512, okay, n bit count. The digital data is converted to analog data using a DAC or digital to analog converter. Now we know that the magnitude of the sine wave is proportional to the voltage at the reference pin. So by changing V reference, I can change the magnitude of the sine here, magnitude of the modulating wave, okay. So at this point I have the reference wave is also the modulating wave, which is a rectified sine wave of same frequency as that of the supply and magnitude variable. The magnitude is proportional to Vref, okay. Now this Vref can come from either from a microprocessor or a microcontroller, okay. This is a very simple scheme to synthesize a sine wave. There are more sophisticated schemes using DSPs are available. Maybe you can read the textbooks, you can find out, okay. So in a PWM converter, I told you that there are large number of pulses, frequency of the predominant harmonic increases, but then the magnitude of the output voltage is proportional to the modulation index, okay. So modulation index can take a value of 1, so the output voltage is always less than or equal to the supply voltage, okay. The power factor of the PWM converter is approximately equal to 1. Now take an application wherein I want a slightly higher voltage than the input, a constant DC voltage is required, okay. I cannot use a PWM rectifier for the simple reason that I want a higher voltage than the input. Second one is harmonics in the source current should be as low as possible, so that I use a smaller filter. Third is the reactive VA or power factor should be very close to unity. Reactive VA should be minimum, okay. How do I achieve this? Okay. You can achieve it using a switched mode rectification, okay. In switch mode rectification, power factor is approximately equal to 1. So the angle between the source voltage and the source current is 0. In other words, for the source, this entire switch mode converter along with the load appears as if it is supplying a resistive load. I will repeat, I said angle between V and I, source voltage and source current, is approximately 0. So for the source, the entire system, the rectifier as well as the load connected to the rectifier appears as if it is feeding to a purely resistive load, okay. So this is the equivalent circuit. Angle between V in and IS is 0. That can happen only if the load is resistive, purely resistive. Please, we are not connecting RE at the output, okay. In other words, power supplied by the converter is not dissipated as heat, it is just a mere representation, or the entire the converter can be modeled as if it is supplying to a resistive load. Power is not dissipated, power is transferred to the output port of the converter, okay. So RE is known as emulated resistance, or this technique is also known as the resistance emulation, okay. Let us see how it works. a simple, a full bridge diode rectifier. I use a inductor L, okay, and a switch here, a diode, and this is the output stage, okay, a capacitor, and I connected a resistor here. Let me tell you one thing, I don't need to connect a resistor here. You can connect some other load to these terminals, okay. What sort of a load we will see sometime later, okay. As of now I connected a resistor, okay. This switch is a fast device, self-commutating fast device. The switch is triggered at a frequency which is much higher than the supply frequency, okay. So assume that I have energized the bridge and I kept the switch open for a longer time. So at steady state, average value of VO1 is equal to average value of V0, because average voltage drop across the inductor is 0 and I am considering dB to be ideal. So average value of VO1 is same as average value of VO. This is case 1. We will see what happens if as soon as I energize the bridge, if I start switching S, that we will see sometime later, okay. Having attained a steady state, I will close S for some time. So what is the equivalent circuit now? When I close S, you see here, this point gets connected to the negative DC bus, or the negative of the capacitor gets connected to the anode of diode DB. So in other words, diode DB is reverse biased, okay. And at the input there is a short circuit, okay. So here is the equivalent circuit, a rectified sine wave, an inductor, switch is closed, so there is a short circuit here, there is open circuit here because diode is reverse biased, voltage appearing across the diode is VO, okay, and a load. I told you that switch S is closed at a frequency much higher than the supply. So what we can assume is that VO1 remains constant at a value which is equal to its instantaneous value, okay. In other words, suppose if I am closing the switch at omega t is equal to pi by 2, VO1 is assumed to remain constant at Vm, and maybe at omega t is equal to pi by 3, VO1 is root 3 by 2 times the peak value, okay. So it remains constant at that particular value when during the switch is closed, okay. So what happens in this loop? VO1 is constant, okay. There is a short circuit here, so voltage across the inductor appearing is constant, therefore IL or current through the inductor increases linearly, okay. And at the load side, capacitor is supplying power, okay. Now I might have said that output voltage will remain constant, and you may say that now capacitor is supplying power, definitely output voltage will fall. Now let me tell you one thing, this switch is closed for a very small duration and it is opened, stored energy in the inductor is transferred to the capacitor and the load, okay. So this process takes place large number of times. So therefore, though the capacitor is supplying power when the switch is on, I am assuming that V0 will remain approximately constant. Is that okay? Though the capacitor is supplying power when the switch is closed, I am assuming that V naught remains practically constant. Okay. So therefore, what is the equivalent circuit when the switch is opened? Okay. When the switch is opened, the equivalent circuit is something like this. Now, inductor current should be continuous. Current starts flowing through dB and the load. This is the equivalent circuit. Okay. Now, when the inductor is charging or when the switch is on, voltage across the inductor is VO1 itself. Okay. And when the switch is opened, voltage across the inductor is VO1 minus V naught. VO1 minus V naught. See, VO1 is when the switch is on, and this time the switch is off. So voltage across the inductor when the switch is off is VO1 minus V naught. Why did I show VO1 minus V naught is negative here? Why? How am I supposed to know that VO1 minus V naught is negative? See the current waveform. When the switch is closed, positive voltage appears across the inductor, current increases linearly. Okay. So at steady state, if the current increases when the switch is closed, current should fall when the switch is opened. Okay. So at one steady state, what happens is I of t at t is equal to 0 should be equal to I of the current at t, where t is the time period. So this value is equal to this, only then I can say that circuit has attained a steady state. Okay. So current increases when the switch is closed, current should fall when the switch is opened. Okay. Now for the current to fall when the switch is opened, voltage across the inductor should be negative. Okay, VL should be negative, only then di by dt is negative. Okay. So voltage across the inductor when switch is opened is VO1 minus V naught. This should be negative. So therefore V naught should be higher than VO1. Okay. V naught should be higher than VO1. But then VO1 is a rectified sine wave. Okay. It varies from 0 to Vm. I told you that V naught is held constant. So that therefore the minimum value of V naught should be peak of Vm. In other words, circuit will function satisfactorily only if V naught is higher than the peak of Vm. Peak of Vm, because this voltage should be negative and VO1 can attain a value of Vm. So therefore V naught should be higher than peak of the input wave. Okay. I have been saying V naught remains constant. Okay. Now what sort of a harmonics or what is the pulsation here in V naught, I will discuss sometime later. Okay. Okay. It need not be a straight line. What it is, we will see sometime later. Okay. So I will explain the principle of operation here. Close switch, store the energy in the inductor, opens the switch, transfer the stored energy in the inductor to the output, okay, to the output. The condition is the V naught should be higher than peak of VO1, okay. So it is nothing but a boost converter, because output voltage is higher than the peak of the input, okay. So if I equate the voltage across the inductor, that is VO1 during this time when the switch is on for D into Ts, where D is the duty cycle. Duty cycle is given by T on divided by T on plus T off, okay, whereas T on plus T off is nothing but sum of T on plus T off, nothing but Ts, the period, time period. So VO1 into dTs is a volt second when the switch is closed, or voltage across the inductor when the switch is closed. Magnitude is VO1, dTs is the duration for which the switch is closed. VO minus VO1 is the voltage across the inductor when the switch is opened, and switch is opened for 1 minus D into Ts duration. So if I equate it, average voltage across the inductor at steady state should be 0, you will find that VO is equal to VO1 1 minus D, okay. Okay. Now how do I choose the value of D? Okay. Is there a strategy? There are two strategies, common strategies, okay, or two popular strategies. There are much more than that. So in first strategy is you keep the switching frequency of the switch constant, okay. Why to keep the switching frequency constant, we will see sometime later. And also keep the duty cycle constant, or the time for which the switch is on, you keep it constant during the entire cycle. Now how do I choose this value of D? You choose the value of D in such a way that the current is just continuous. The inductor current is just continuous at omega t is equal to pi by 2, okay. In other words, see, here is VO1, the inductor current is just continuous at omega t is equal to pi by 2, in the sense just prior to closing the switch, current is just touched 0, current increases, okay. At this instant I am opening the switch, say after D I have to open the switch, current falls, okay, and it has just touched 0, immediately I am switching the device again. So it is just touching the 0 axis, so I am calling it as just continuous at this point, okay. You find here, you see the current has become 0, and for some time current is remains 0, okay. See here, current is 0, and after some time looks like switch is closed, current increases. So for finite duration switch is open, or sorry, for finite duration there is no current flowing through the inductor, okay. Whereas here near the peak, okay, current just touches 0, current just touches 0. Why are we doing this? Why are we doing this? I will make another statement, just listen to me. if the current is discontinuous at omega t is equal to pi by 2, it will be definitely be discontinuous in the remaining period. Okay. If it is discontinuous at omega t is equal to pi by 2, there will be durations of zero current in the remaining periods. Okay. This is for sure. Why am I saying this? Okay. Now, the VO1 varies sinusoidally here. Okay. In this circuit, if you see, L is constant, duration for which S is closed is also constant. Okay. So therefore the peak value of the current is given by VO1 divided by L, and we assume that switch is closed on and off at a very high frequency, and during that period VO1 will remain constant. Its value is proportional to the instantaneous value of VO1, but then VO1 itself is varying sinusoidally, therefore the peak value of the current will follow a sinusoid. Okay. See, the peak value of the current will follow a sinusoid, because switch is closed for a fixed duration. VO1 is proportional to the peak of, VO1 is proportional to the instantaneous value of the sinusoid. Okay. So therefore the peak value of current is proportional to VO1 itself. Okay. Since di by dt is proportional to VO1 when the switch is closed, di by dt is maximum when omega t is equal to pi by 2. Okay. di by dt is VO1 divided by L. So VO1 is maximum at omega t is equal to pi by 2. When this negative di by dt is maximum, in the sense when I close the switch, current rises very fastly when omega t is equal to pi by 2. What happens when I open the switch at omega t is equal to pi by 2? di by dt is minimum when omega t is equal to pi by 2, in the sense minus di by dt. Okay. Why so? So this slide, whatever that I explained just now, I peak is VO1 divided by L into dt. I peak is proportional to VO1. So maximum value of I peak is at omega t is equal to pi by 2. DIL by dt is maximum when the magnitude of VO minus VO1 is maximum. So VO minus VO1 is the voltage appearing across the inductor when the switch is opened. This is the voltage appearing across the inductor when the switch is opened. So negative di by dt is maximum when this is maximum. V0 remains constant, whereas VO1 is changing, it varies 0 to its peak value. Therefore di by dt is maximum when VO1 is 0. In other words, the rate of decay when the switch is open is maximum near the zero crossing, because at that time VO1 is 0 and rate of decay of current when I open the switch is minimum at the peak. Okay, at that instant, see, this difference is minimum. V0 is held at constant, VO1 is equal to Vm at omega t is equal to pi by 2. So therefore this difference is minimum when omega t is equal to pi by 2. This is the voltage appearing across the inductor when the switch is opened. So if this is minimum, rate of decay is also very slow. Or when this is maximum, which happens when VO1 is near the zero crossing, positive or negative, the same. So this is maximum when VO1 is at the zero crossing, therefore the rate of decay is also maximum near the zero crossing. See in this figure, see, near the zero crossing, Vi is, or the instantaneous value of VO1 is very small near the zero crossing. So therefore when the switch is closed, the forcing function is very small. Okay. So when I near the zero crossing, since the forcing function is very small, the rate of rise of current is also low. Okay. See here, current near the zero crossing, current increases very slowly, whereas when omega t is equal to pi by 2, the forcing function is at the peak, okay, is equal to Vm, so current rises very fast. Okay. When I open the switch, the voltage across the inductor is maximum near the zero crossing. Okay. So therefore negative di by dt is maximum here. So current instantaneously current decays at a much faster rate compared to omega t is equal to pi by 2. So current rises slowly, decays faster, whereas here current rises very fast, decays very slowly. Okay. See here, current increases slowly because forcing function is very small. VO1, instantaneous value of VO1 near the zero crossing is very small. Switch is closed for a fixed duration. Okay. Increases very slowly, dies down very fast because VO minus VO1 is maximum near the zero crossing, whereas here rises very fast because forcing function is at the peak, decays very slowly. Okay. So therefore what I come back to the statement which I made before is that if the current is just continuous here, current will be definitely discontinuous in the remaining period. Why? Here current rises to a peak value, maximum value of the inductor current is at omega t is equal to pi by 2, okay, and it decays very slowly. Okay. It has a maximum value, decays very slowly, and I am telling that current is just continuous at this point. So what will happen here? A very small current decays much faster. So therefore if the current is continuous at this point, there will be durations of zero current in the remaining period. Okay, durations of zero current in the remaining period. So if the current is continuous near omega t is equal to pi by 2, it will be definitely discontinuous in other regions. Okay, because maximum value of current decays slowly, but it becomes zero, just touches zero. If that is the case, when the current is minimum and dies down much faster, there has to be a zero current period before the switch is closed the next time. Okay. Now you may ask, why not the current be just continuous near the zero crossing? What will happen if the current is just continuous near the zero crossing? See here, that means near the zero crossing it just touched zero and immediately the switch is closed again. So what will happen? I said near the zero, peak value of the current is very small because in instantaneous value of the input voltage is very small, it decays very fast, okay, and immediately the switch is closed near the zero crossing. Now what will happen as VO1 increases, mind you, from 0 to omega t is equal to pi by 2, VO1 increases sinusoidally. So the peak value of current also increases, but then as omega t increases towards pi by 2, it decays very slowly. Okay. So a small value of current, it has just touched 0 here. So definitely in the second cycle it will attain a much higher value than this, but then rate of decay is slower here, so it will not touch 0. Okay, I will repeat. See, I have a very small value of current and it touches 0 here because it decays very fast. When I close the switch for the second time, since VO1 has increased, this peak has increased, but then rate of decay is slower compared to this. Rate of decay is slower compared to this period. So when I close the switch for the third time, there will be some current in the inductor. Okay, current will not become 0. Now VO1 has also increased, peak value further increases, but then again dies down at a much lesser rate compared to the previous. So this current increases. So in other words, you may have a situation wherein current goes on building up. Okay. See, it was just at 0 when instantaneous value of the input voltage is 0, approximately 0, sorry. A very small current decays fast, it just at 0, but in the next instant the peak value is higher and decays slowly, so it will not become 0 at all. Okay. In the third case, it will attain a much higher value, decays very slowly, so this current will be much higher than this. So it so happens that it goes on building up and it may saturate the inductor. Okay. So there are very good chances of inductor getting saturated as you go towards omega t is equal to pi by 2. That is the reason if the current is just continuous at omega t is equal to pi by 2, it will be definitely be discontinuous in the remaining period. Okay. And if the current is just continuous at omega t is equal to 0 near the zero crossing, it may so happen that current will build up and may saturate the inductor. And if the inductor saturates, you may be able to see the smoke coming out from the converter. Why? If the inductor is saturated, there is no rate of change of current. Current is limited by the internal resistance of the inductor itself, which is very small. For all practical purposes, we neglect this resistance. So the relationship is I is equal to VO1 divided by small r once the inductor is saturated. But then unfortunately again VO1 goes on increasing when I go towards pi by 2. So you may see the smoke coming out from the circuit. Okay. So that is the reason you choose a value of D, the current is just continuous at omega t is equal to pi by 2. Now which is the second most common technique? See, here is it. Okay. I will take a rectified sine wave, the input, or I synthesize a sine wave, rectified sine wave. Okay. I have whose frequency is same as that of the supply. I will call this rectified sine wave as Iref star, as the reference current. I will call this waveform as the reference current. Then I will take a small band, a upper band, which is shown in this dotted line, which is the IU star, an upper band, and a lower band, a IL star. Okay. Now it is approximately a sinusoid, isn't it? If I control the current within this hysteresis band, at any given time, if the current is within the hysteresis band, I can say that inductor current is approximately a sinusoid. Okay. So see, I have controlled the current within the hysteresis band. So this band is the lower and this may be the upper. It looks approximately a sinusoid, So what do I need to do? Take a reference sinusoid of desired magnitude. How to choose the magnitude? I will address that issue. Take a upper band, IU, and a lower band. Measure the inductor current and control it in such a way that this inductor current always lies within I upper and I lower. Okay. How do I control the inductor current? We know that when I close the switch S, current through the inductor increases, and when I open the switch, current through the inductor decreases. So what I will do is, when the current touches the lower band, I will close the switch. Current starts increasing. When the current touches the upper band, I will open the switch. Current starts decreasing, and I will continue this process. Okay. So therefore, I have a current, I am controlling the current flowing through the inductor, hence the name current controlled switch mode rectifier. I have taken a hysteresis band. So this technique is also known as hysteresis current control technique, hysteresis current control technique. Okay, current is controlled within the hysteresis band, and it looks, the inductor current is a rectified sine wave. This inductor current is the same as the source current. Okay, so in this circuit, inductor current is same as the source current. Whatever the current flowing through the inductor should come from the source. Okay, so if it is a rectified sine, source current is a sinusoid. Okay, so this Is is in phase with Vi. Okay, therefore displacement factor is unity. Current is a sinusoid, therefore RMS values is same as the fundamental component. So the power factor becomes approximately equal to 1. Okay. So the entire bridge along with this resistor load appears like a resistive load to the source. Since Is is a sinusoid and is in phase with Vi. Okay. In both the cases, even when I use a fixed duty cycle, okay, the peak value of the current follows a sinusoid. Peak value of the current follows a sinusoid even in fixed strategy. But then it may have a higher frequency components. Now these higher frequency components can be filtered using a very small L and C. Okay. Now let me tell you one thing, the frequency of the components that are present in the source current are proportional to the switching frequency, and this switching frequency is much higher than the input source. So I require a very small L and C to filter out this higher frequency current. So source current is approximately a sinusoid and it is in phase with the input voltage. See in this is a fundamental component, is a sinusoid, may have a higher frequency component, they get filtered out. So I have almost a sinusoid which is in phase with the input voltage. The power factor is 1, so the entire unit looks like as if the source is feeding a resistive load. Okay. Now if you see in the circuit, smaller the band, better is the source current waveform. Smaller the band, it looks as if the current is a sinusoid itself. Now this band is very small, then the current will look like a sinusoid. But then if I reduce the band, I may have to switch at a much higher frequency, because small band, current touches the lower band, I close the switch, current increases, the moment it touches upper band I have to open the switch. Since this band is very small, device is switched on off at a much higher rate. In other words, the switching frequency depends on height of this band. Okay. Smaller the band, higher is the switching frequency. Smaller the band, better is the source current waveform. So there is a trade-off. Okay, if you want to have a superior current waveform, reduce this band, but then switch S is switched at a much higher frequency. Maybe converter efficiency comes down, temperature may increase. Okay.